Okay, so hi everybody, welcome to this course on perturbation methods, which is a course I teach at the University of Liège. This actually video is the first one of a very long series, and we'll cover some general concepts of what we mean by perturbation methods. So just to start with something rather illustrated, I decided to just pick an example at random. Almost at random, it comes from solid mechanics. This is a problem I enjoy quite a lot because, well, as some of you might know, I'm mostly from civil engineering or structural engineering. So solid mechanics is something I master quite well. But of course, throughout this course, we'll discover many other problems from fluid mechanics, for instance, and even from other different theories in physics. So let's imagine we have to solve a simply supported beam resting on two supports and at the same time resting on a set of springs which are used to limit the deflections of the beam between the two supports. This beam is also subjected to an external applied load, P, and we would like to determine the deformed configuration of that beam, which is represented here by the black line. And the transverse displacement is modeled by V as a function of the abscissa X measured along the beam. And so I skip, one should go to solid mechanic course to come back to the establishment of this equation, but I skip this. Just keep it as an equation by now. The governing equation is made of three different terms. The first one is related to the bending stiffness. Second one is related to the stiffness of the springs. And the third on the right-hand side is the applied loads. This equation, of course, is a fourth-degree differential equation. It comes with boundary conditions. And if the beam is simply supported, then the boundary conditions are something like this, where L, capital L, is the span of the beam. Okay, this problem is definitely not difficult at all because there's even an explicit solution for that. If we go to calculus would say, okay, just write the characteristic polynomial for that equation, ei z to the 4 plus k times z, then determine the values for z that cancel that polynomial, which is quite simple. Sorry for this, which is quite simple in this case, because you see this is only the fourth power of z that is involved, so we have four simple solutions. And then I skip details because that's not the aim of the exercise here. You can construct the homogeneous solution of the problem by using the corresponding solutions to the exponentials of those roots. And that's something like this that you would obtain. So the homogeneous solution, which is composed of four terms, plus a particular solution. The constants of integration can be used once you have added all these five terms together and then consider the boundary conditions. All right. We could imagine from now right away that this problem is a linearized version of something that could be more realistic and which could be slightly nonlinear. So imagine that k is equal to a constant plus a small perturbation. This is called the perturbation. And we would like to know how much this perturbation affects the solution that we got in the unperturbed case. All right, so the unperturbed case is the case that we obtained without the perturbation. Okay, that's something that is very important. Just by setting this small parameter epsilon equal to 0. Epsilon is a generic parameter that is typically positive, and we write it this way. It is much smaller than 1, meaning that this is a small number in a problem, typically 10% or even lower, maybe it could be 1%, or if it's even lower, that's even much better for us. Because as you will see, the asymptotic series that we are going to derive later depend on the smallness, on the quality that we get depends on the smallness of this parameter. All right, and so the unperturbed problem, if it can be solved, then this is fine. And in this case, it can be solved by means of calculus. Definitely here, as soon as you add this perturbation, there's no closed form solution any longer. So in the perturbed version of the problem, there is no analytical solution. I mean, no exact analytical solution. And so, of course, there's a long tradition at our university in numerical methods and numerical techniques. So, of course, you would be tempted to solve that equation by means of a appropriate numerical method. All right, and so if you use a numerical technique, it could be, for instance, finite elements, numerical method. It means that you're already in the field of applied mathematics. I don't want to say this is the same as engineering, but for us as engineers, this is exactly what we are interested in, because we want to solve real problems, and in real problems, usually we are quite far from the ideal case, which is something that we can solve analytically in a very simple manner without any weird perturbation or difficult terms that are hard to deal with. You can think of this kind of complexity in the form of the equation itself, like this, by adding terms that are highly nonlinear or difficult to handle in an analytical manner. Or you can also think of complexity of realistic problems, because, for instance, the body on which you want to study a governing equation has a geometry that is perhaps quite complex. Just imagine a solid on which some loads are acting, or imagine the flow in a channel, or imagine the flow around a rocket, that kind of stuff. So the problem that you solve in principle might be really difficult because of its geometry. And usually we are quite far from what pure mathematicians in mathematics usually deal with. They usually deal with exact analytical approaches, and they care about uniqueness of solutions. That's probably a little bit too much of a picture we give to mathematicians. And much more than what's the actual solution if the problem is a little bit more complex than what we can solve. Numerical methods, they might struggle from time to time, and I'm sure you're aware of that. So the other teachers who do teach numerical techniques, finite element methods, I'm sure they highlight the different conditions in which numerical methods might struggle to provide good results. I'm going to show an example just in a few minutes. And so sometimes it is good to see the other side of the coin, which is something that is not so famous in applied mathematics, which is something that would provide other approximate methods. Because numerical methods definitely are approximate as soon as you decide to discretize a domain and write, for instance, a weak formulation of a governing equation. This is an approximate method. I understand, of course, that if you decide to decrease the size of your mesh, it's supposed to converge to the exact solution. That's what you expect. But there are other ways to do so, and perturbation methods is another kind of approximate method that belongs to applied mathematics. Exactly as the usual numerical methods require the mesh size to go to 0 in order for the problem to converge to the exact solution. Perturbation methods will require the small parameter that we have introduced to go to 0 if we want this approached solution to converge to the exact one. And this is something that makes the difference between applied mathematicians and mathematicians, is that applied mathematicians, I would say, they need to provide sometimes ad hoc solutions or appropriate solutions to the problems, even if the result they get is not the exact solution of the problem. Okay, and perturbation method is something that is much more analytical than numerical, in fact. All right, so it could be considered, because it is an analytical approach, it could be considered kind of halfway between mathematics and applied mathematics. It's quite unusual to use perturbation methods, but you will see throughout this course that this is something that is really powerful, and when this is mastered, can really help in solving problems. All right, and so why are numerical methods and perturbation approaches things that are kind of complementary? They are complementary because in some cases, if the problem you want to study becomes ill-posed or ill-conditioned, or in the sense that the conditioning number of the problem could be the condition number of a stiffness matrix in this case, is such that one eigenvalue at least is very small, then the problem that you're looking at might behave in different manners, all right? So in this case, we could imagine, for instance, that a bending stiffness is something that goes down to 0 and becomes really, really small. So it means that in the three terms governing the equation over here, the first term is something that would become much smaller than the others. Well, if you do this, if we assume a case like this one, in fact, the deformed configuration of the beam will provide something that looks like this. Oops, very hard to represent. And then 0 everywhere. That's for a small bending stiffness. And if you make the bending stiffness smaller and smaller and smaller, you will notice, in fact, that the area over which the displacement V, the transverse displacement V, is significant, actually this area over there goes down to 0. And if it goes down to 0, this is something that becomes really hard to capture with any grid-based method, any numerical method that would require the meshing of the initial domain into small elements. However, if the bending stiffness EI comes close to 0, then we can reconsider the problem, say that this is a small number, and try to see if we can solve the problem with in an approximate manner with perturbation methods. And so as soon as there is a small number in the problem, small number could be a small problem parameter, could also be a small geometric indicator of the domain on which you need to solve the problem. So as soon as there is a small number in the problem, you can simplify by using a perturbation technique. On the opposite side, when there is no small number, or when all quantities, that's what it means in fact, all quantities involved in the problem are of order 1, then the problem is definitely well posed to be solved with a numerical technique. All right, so we see here that we have two different things. Perturbation technique as soon as there is a small number in the problem, and when there is no small number in the problem, we should use numerical methods. And this is how and why we can see them as two complementary approaches to problem solving. All right. So, perturbation methods, as I said, needs or means there is a small parameter in the problem. What do we mean by small? If we mean by small, that's what I said, we introduce a small number or a small parameter, needs to be small compared to 1. Okay, and this is something we are going to write every other day as soon as we work with perturbation methods. All right, so this is really important. Every time you start with a problem where you expect a quantity to be small, you need to make it explicit, make it clear, introduce a small number, which is chosen in an arbitrary manner, then proceed with the derivation following what we're going to learn together in those perturbation techniques, and then get rid of epsilon, come back to the original properties or quantities of the problem. Okay, so it means that we need to get this small number. What do we compare it to? We compare it to 1. A number that is compared to 1 should be unitless. So it means that as soon as we're talking about small number, we're talking about dimensional analysis. All right, and or comparison of terms with respect to each other. Remember what I said before? I said, let's imagine the bending stiffness is something very small. This one, the first term here, is smaller than the other two terms. All right, we can put it in a different manner. We could put it in a different manner. We learn together through few examples how to rewrite governing equations in a dimensionless manner. That's probably something you know already. I'm sure in dimensional analysis, the Cauchy-Buckingham theorem is something that you all know, and that's something we probably touch a little bit when we want to write a dimensionless version of the problem. And if you want to do it over here, in fact, what we would get, I skip details because there will be plenty of chances to do it together. We'll certainly redefine y as a dimensionless quantity, which could be, for instance, the transverse displacement, v, divided by a reference applied load divided by the stiffness. And if we use this to redefine the problem, we can also redefine x as xc times L, where L is the total span. And we notice actually that the governing equation could become something like A times the fourth derivative of y with respect to xc this time, plus B times y is equal to 1. And we have two boundary conditions. The boundary conditions would be y0 and its second derivative is equal to 0. and y of 1, second derivative of y is equal to 0. And when we do this, we see that a and b are two problem parameters, while y and xi have no units. Okay, so we have rewritten the problem. Y and xi have no units. We have rewritten the problem in such a way that it is fully non-dimensional. All right, and so if you want to focus on areas where you want to say, for instance, okay, let's consider what happens when x is close to the left support, so small, near 0. Okay, of course you can't write something like x is close to 0. All right, that's not something we're going to work. We will say we want to study x is of the order of magnitude of epsilon. X has order of magnitude of epsilon. That's what we mean. If you want to say that x is near the right support, we won't write something like this. We'll just write x is 1 minus epsilon. Okay, it means we are just a little bit before the support, in the neighborhood of the support. Okay, that's things we're going to derive or to use or write together a little bit later. There are ways to do that. All right. Next, another detail which is summarized by this: small means large. Small means large, indicating that in a problem, let's take it for instance, as we said before, let's imagine the bending stiffness EI is a small number. And so at some point we could get an equation which looks like this: plus B times Y is equal to 1. Okay, and so if the bending stiffness is small, this is what we get. In the unperturbed case, as I described before, what do we have? Okay, keep in mind, unperturbed case means just that there is no perturbation. We end up with by is equal to 1, so we can solve y is 1 over b. Okay, that's when epsilon, the bending stiffness, is very small. What if it's very large? Well, if this is very large, instead of using epsilon, we'll certainly use 1 over epsilon. And so the problem could be conceptualized or idealized in this manner. We don't like to divide by epsilon, especially in the initial governing equation. So what we can do here is to multiply everything by epsilon to the 4. We end up with this. And finally, in this case, the unperturbed problem, I mean when epsilon is equal to 0 again, is the fourth derivative of y is equal to 0. Of course, to be solved with boundary condition and so on and so on. Okay, just to say that if you want to identify in a problem that a certain quantity or a parameter is small, this is fine. Usually it would come in the equation in something that looks like this. But if you want to say that some number is large, this is quite unconventional to write it this way. So we just rewrite the problem in this manner. So say that epsilon still is a small number and end up with something like this. Okay, what would be really unconventional, and this is something I don't want to write. I don't want you to write because I think it's a bad option to take. Would be to use a large number. I use capital M to indicate this is a large number, multiplied by the fourth derivative of y plus by is equal to 1, okay? And this means large. As soon as you see that, you need to determine how large is large. That's also something we're going to discuss in the first few examples. And for instance, say in this case that m is large because this is the inverse of a very small number, and then proceed further until you can rewrite the problem in that format. All right. Finally, before closing this first video, I need to introduce a last little detail. Is that small is actually not the same as negligible. Okay, we will understand this by means of an example in the very next video. Small is not the same as negligible because usually when a quantity is small, so far, or I would say even in the standard way of approaching problems as an engineer, we usually say, okay, there's a small number, so okay, fine, let's just neglect it. Okay, for instance, we can come back again with the problem where the bending stiffness of the beam is something that is very small, like this. Okay, so I rewrite this governing equation and assume the problem is such that we have a small bending stiffness. So this one is small. And if you would neglect this value because you just want to make it explicit that the bending stiffness is something small, you're not interested in the bending stiffness, what do you end up with? You end up with that equation. Y is equal to a constant. B is something that is given, right? It's not necessarily equal to infinity, for sure. This is a finite number. And so the question here is, how do you meet the boundary condition? There's no way to do it. And so what you would find somehow is a solution that is not fine, okay? So first, when you do neglect things that are small, starting from a certain governing equation, there is no guarantee that the equation you end up with is something you can solve, okay? So that's a first problem. And second, even if the equation could be solved, it doesn't tell you at all the influence of this small number. And if you put this small number in the problem, or if you recognize this is some sort of physics that is there, that exists, but is small, you could still be interested in understanding how it affects the unperturbed solution, right? And so small doesn't mean negligible. And if we had to put them, these two qualifiers, let's say, on a scale, we would say neglected, meaning epsilon is equal to 0. Small, the perturbation is much smaller than 1. This is usually a positive number, so put it this way. And we're going all the way to exact solution or exact formulation of the problem, where epsilon is something that is not necessarily small, all right? And so really small is something that we can see in an asymptotic manner as epsilon, the small number, goes to 0. And so if we knew, for instance, a parametric version of the solution of the problem, as a function of epsilon, or in the example that I considered before, it should be a function of xi and epsilon. I can even write it this way because the solution of the problem is y. What we mean by small here is some sort of asymptotic expansion can be a series expansion. We're talking a lot about series in this course. Asymptotic expansion of y as epsilon is a small number. All right. Okay, and so I will start the next video by saying this again, and this one will close the first video. We don't want necessarily to solve the exact problem, because this solution on the right is something that might be quite tough to get, especially if the problem you want to solve at the very beginning is a problem that has some important nonlinearities, small but important nonlinearities that make it such that the determination of the exact solution of the problem is really, really, really tough. All right, so this is something that is hard to get. And perturbation methods, what do? They aim at providing this asymptotic expansion without knowing a priori the exact solution. Okay, that's all about what we want to do in this course about perturbation methods. All right, so speaking enough for this introduction, I suggest now to start in a few minutes with a few examples. And before closing, I'd just like to highlight the fact that these lecture notes have been prepared by those beautiful and wonderful lecture notes prepared by Hinch under the name Perturbation Methods. This is a booklet, a small book, soft cover. I would definitely recommend you to buy this one because this is a very good book, and it's been edited by Cambridge Press. All right, so see you soon, and I hope you keep going with the following video.